So my name is Chris. You guys can call me Chris. I happen to be Dr. Greg or Commander Greg. I'm in the J39. I'm actually the J39 here at HOA. And I got my PhD about a year ago. I'll go over some more details about me. And I just want to let you know in here, it's all first names. I mean, you can call me whatever you want, but we don't need sirs. We don't need any of that. Just we're here to learn, and we're not here to, play the military game. So fair enough? All right. And if you want me to call you by some other name than what your first name is, then that's fine with me too. Just let me know, and we'll go over there. So class in here, 1715 to 2015. Anybody besides me work at least until 1700 every day? Yeah, a few of us. So if you want, I'm certainly up to pushing this later if people think that would be worthwhile, but I'd rather have it be kind of a majority thing. Hey there. Yeah, I already took roll. The only person who's not here, James Stark, or Michael Stark, who you said was going to be a little late.
And then that was 4-2.
And he said he's not going to be here. Well, anyway, that's how I put him down. But okay, everybody knows Christian. Probably the guy who signed you up for this. No worries. Cheers. Thanks, Christian. All right. Okay. Well, he didn't take it. All right. Well.
So, Chris,
yes.
So we're using this book Mondays and Saturdays, and the other book on Sundays.
Yes, more or less. Although all the concepts are in that book. You want to hold it up? That's the big one, the thick one. We'll get into the details of the book. I actually think this is a great book. I don't know if you guys hopefully got a chance to read the first chapter or at least glance over it. I know reading's always kind of, it's one of those things where you get to it and it's kind of takes a while. But do the best you can to at least scan over the chapter before you get into class. Because if you see it a couple times, it makes it a little easier. As you all know, you've got the giant book. Technically, we're supposed to go through the entire book in 8 weeks. Now, I've taught this class, or something similar to this class, the physics portion of it anyway, a number of times. And getting through the entire book in 8 weeks is like twice the material that I would normally cover in like an entire year of teaching like regular physics. So it's going to be fast and furious, but we'll get to the details of how that's going to affect you guys later anyway. Okay, so let's see. This is me. I am a Naval Reserve officer. Been in HOA about, well, let's see, how many days was it? 4 months and 8 days or something. Not that I'm counting. I can send you my spreadsheet tracker if you'd like. We went to NIAC together too, didn't we? Yeah, Tom and I went to NIAC together way back when, it seems, at this point. And I'm here through next October, but we'll make it. We'll make it. So for the last 4 years, I said I've been a reservist. This was actually when I went to graduate school. I got my PhD in computer engineering, actually, and I was the CO of a reserve unit in North Carolina before they voluntold me to come here. And so I worked on that. Before that, I was a high school physics teacher in Brookline, Mass. Anybody from Massachusetts here? All right, where are you from?
Boston.
Oh, no kidding. All right. Yeah, I taught in Brookline, lived in Boston for overall about 8 years so far. Enjoyed it. Lived in Virginia as well. And then I also taught in California, Santa Cruz. Anybody from California?
I was born in Santa Cruz.
No kidding. Love Santa Cruz. I never should have left. Never should have left, but live and learn. Anyway, so that was what I did there. I also got a master's in education. So I did about 7 years of high school teaching, mostly from the same guy that wrote the book by the same guy that wrote your book. So I'm kind of familiar with most of the stuff, at least the first half of the class, for what it's worth. So hopefully that part at least will be extra smooth. And then before that, I was in active duty for about 5 years. I guess 7 total, really, altogether. But 2 years I was in Australia. Best job of my entire life. Can't imagine a better place to be stationed. It was pretty phenomenal. It's part of the reason I got out of the Navy was because I realized that I'd never find another job as good as the one that I was in. I was looking at another ship or something and thinking, not really my thing. And then before that I was in San Diego, another amazing place. Probably just about as amazing as Santa Cruz, to tell you the truth, but it was. I was there for about 3 years doing direct support trips, meaning I'd go out for 6 months at a time on cruises and do workups and all that. Got to see a zillion places in the Pacific, Singapore and Hawaii and Australia and Muscat, Oman and Jebel Ali and Kuwait and all that kind of stuff. And it was great. So enjoyed a lot. Enjoyed my time in the Navy. You know, reserves isn't quite the same. But how many people are in the reserves? One reservist? Everybody else is active, no kidding. And then you're a civilian, Nicholas, correct? Okay, cool. In high school, or whatever equivalent degree you might have gotten, did you guys raise your hand if you took a physics class? 1, 2, only a couple of you guys. Okay, for those of you who took physics, a lot of this stuff may be review because it's, as we'll talk about, it's conceptual, which means that we're not really going to do too many calculations, believe it or not. A few here and there. I know math for some people is a little tricky, I understand. But really, this class is not about the math. If you did take a physics class at one point, you might have remembered like just doing problem after problem after problem. It's like math class, problem after problem. And honestly, that's not really the best way to learn physics. I mean, you can learn how to do problems, but if you don't really understand it, that kind of gets in the way of you know, going forward in the type of class. So for what it's worth, if you didn't take physics, or how many took chemistry? 1, 2, 3, okay. Most of you guys took chemistry. Chemistry is actually going to come after physics. Talk about why in a minute, why that's the case, in this class anyway. How about biology? Biology, most people took biology. What do you guys who didn't raise your hands? Did you go to high school? No, okay, there you go. This class is not biology. Physical science is not biology. We'll get into the difference between physical science and the other sciences in a little bit as well. So you're all working on your undergraduate degree. How about earth science? Anybody take that? No, that's not as much. That's not taught as much anymore, believe it or not. And then astronomy. Anybody happen to take an astronomy class? You did? Yeah, astronomy is a cool class. And we get to the last quarter of the book's all astronomy, which is cool. And astronomy is not just like what constellations there are. Believe it or not, there's a lot of stuff. Now, again, this is conceptual. A lot of astronomy does involve kind of big thinking ideas, but again, we're going to leave it at the very conceptual lesson, so you come out of here and you'll be able to talk a little astronomy, and we're not going to worry about doing tons and tons of problems. So that's good. Let's see. You guys are probably pretty busy, and taking classes is a priority, but you do have a 9 to 5 job, or an 8 to 5 job, or a 6 to 5 job, or whatever, right? So I understand that. And I am not going to sit here and make you guys do so much work that all your off time is doing work. Is anybody taking 2 classes right now? Yeah, you guys are crazy. 2 classes is crazy, but with a full-time job, but I understand. I do not think you'll be overtaxed in this class. Let me put it that way. We're going to talk in a minute about how you want to do the homework. I'm actually a little bit flexible on how that's going to be. So we'll get to that in a few minutes. And as we already talked about, a couple of you guys are leaving before class ends, so you guys definitely get together with me. It doesn't have to be today, but sometime soon to talk about the schedule. We'll go from there. Any questions about who you guys are? No? Okay, I won't make you guys go around and tell me all your jobs. Maybe sometime later. But I tell you what, at some point during the class, you'll probably stand up here and give a 10 to 15 minute presentation. Don't be afraid. But at that point, you can introduce yourself and say, you know, I work here and blah, blah, blah. So there you go. Okay. Now, what is this whole physical science stuff, right? So physical science, physics is almost says it in there. Physical science is what we call the hard sciences in many ways. And it's not hard in difficult, but hard in the science itself has a very mathematical way of being defined, and it's very it has the nice properties that we can do very concrete experiments most of the time, figure stuff out, write it down, get theories from that, and prove things by doing empirical experiments. And by empirical, I mean you're actually watching something like do something. And it's slightly different than the biological sciences, which are considered a little bit softer. Again, not that they're less difficult. In fact, I think biology is particularly difficult. But it's not as concrete as the physical sciences. So we are going to talk about 4 different branches, which we'll get to in a minute, and we're going to go through a lot of material this course. But again, it's not going to be too much pressure. It's just going to be I really do want you to understand this, right? You guys aren't science majors. You're probably taking this because you have to. Some people are taking it because they really want to, but it might be checking a box or whatever. My point is, if you guys understand this stuff conceptually to the point where you can have a discussion about it and not say anything wrong, because I guarantee you some of you guys have some ideas that are actually incorrect about the physical world around here, and we're going to change that, hopefully. Okay, we're gonna work to make those ideas truthful, which is not necessarily the case. And by conceptual, again, that means there's these ideas that we will understand, and we're not going to worry so much about doing formulas and writing the stuff down. It just doesn't make sense to do that if you're just trying to understand what that's all about. Okay, so that's what this course is about. Okay, let's talk about a couple class logistics. Hopefully, you guys all grabbed a syllabus. Hopefully, I don't think I have one myself. Everybody get one of these? Okay, it's like 4 pages of kind of dense stuff. The big thing, as Christian said, the classes for the kind of teaching part of it are Mondays and Saturdays. That's why we're here now, 3 hours. Technically, the labs are 4 hours on Sunday, which is a lot of time. I don't think we're going to have labs ever really go 4 hours. Just to put it out there right now. It may, but I think the labs are going to be, they're going to be reasonable, not like super, super long. You'll see on here there's some projects due. We'll talk about that in a minute and how we're going to go about that. As I said, I'm a little flexible on how that goes. And we go all the way until Saturday, the 10th of May. We do have a midterm in there, mid-April. And and by the way, April 27th, Tom and I are going to be a little happy because we're halfway done at that point. Yeah, so halfway done like 2 days before. Not that I'm bitter about being here or anything, but you know, it's the way it goes. Okay, so just a kind of overall schedule on the front page. Second page, again, I don't think I have to tell you guys this. Attendance is mandatory. If you have to miss class, just let me know beforehand. An email or a phone call or whatever, and say, hey, I'm going to miss class. I'll watch the video, or whatever. Somebody will tell me exactly what happened. I've read the chapter. Blah blah blah. I'm flexible. We all have hard jobs. I may have to miss a class here or there. We'll try to reschedule. But it was a bit tricky convincing the J3 that I could actually teach this class. So for what it's worth, he's got his eye on me. As I said right at the beginning, you got to read the chapter, or at least skim it. I don't care if it's like tedious or annoying. It's a good book. It's very simple in the sense of he doesn't use big words. He doesn't use lots of formulas. It's the kind of thing that I know you guys can knock right out. And don't just try to read it the day of class, like, oh, I'm going to lunch, I'm going to read the textbook. Just over the 4 or 5 days between, or well, 2 days in some cases, between the classes, read the chapters that are assigned. All I ask as far as the kind of main big stuff. Okay, let's see. So, question. How do I get an A in this class? You guys all want an A, I'm sure. If you show me that you can do the best you can, you will probably get an A. Okay, and by that I mean you do the reading, you participate in class, you do whatever homework we talk about, you do the projects, do okay on the midterm, final, done. It sounds like a lot, but it's really relatively straightforward. Okay, read the textbook, I already talked about that, participate, 2 exams. So there's, anybody looked in their book, you've got a little card in the back, I think, or the front or something like that. I think it came with your textbook. It should have anyway. If it didn't, let me know. Hold that one up if you could. Okay, thanks. Sorry, what? Alan, right. You know what? I can't even read my own handwriting. I was going to say Alvin. Alan. Okay. Thanks, Alan. The card gives you access for the whole course to this site called masteringphysics.com, and it's got a ton of stuff on there. It has your textbook. So if you don't want to be sitting there and work and reading your textbook, and you just happen to sit in front of your computer, you can log on and go through the textbook there if you want. It also has practice problems, It's got little interactive things, some which we'll go through here, and I think you'll get good use out of this. Okay. Have fun producing your project. The projects that we'll talk about, I think you'll get a chance to really dig in a little bit to some subjects. Have a lot of fun with that. If you have fun doing your projects, you'll have fun with the one presentation that I give you, hopefully, and then I think you'll enjoy it more, and you'll just do better if you try to enjoy it. And then again, make sure you understand the syllabus. Nobody will come in here not knowing when the midterm is and so forth. I don't expect you to do that. Okay? Question on how I get an A? Okay? I won't go through how you get an F, but if you don't do all these things, that'll be the case. I don't expect anybody to do poorly in here. Let me just say that up front. Try hard, you'll do fine. Okay? All right, syllabus, you've got one in front of you. I'm gonna put up the website here. Let's see, if you want, I think it's on the front of the syllabus I handed out too. The website's gonna have the syllabus, obviously, for the lab and for this. It's going to have the lecture slides, these ones. So you can go through those again if you want. It's also gonna have the video once I figure out how to transfer that in, and that'll do. It's got information about how to reach me, all the outline, and so forth. Okay, and the grading scheme, which we still have to talk about. Okay, if you miss class, I already talked about this. If you miss class, just let me know. I know where you guys live. Okay, I can find you if you just start skipping class. And trust me, there's only 8 weeks, and you miss 1 or 2 classes, you'll just be behind, and it's not going to be good. Okay, class are videotaped. Late work. If we have something due, it's due on some day. If you're not going to have time to do it, don't come to class and say, sorry, I didn't get my work done. Just email me and say, hey, Chris, I can't get this stuff done. I had to do this, blah, blah, blah. The mongoose ate my homework, whatever. Right? Okay, so you got to be, just let me know beforehand so that we can all be on the same page. Just makes it easier all around. Okay, and as I said before, if you're going to miss class, let me know. I might miss class sometimes. If I'm going to be late someday, like my boss says, you got to stay for this meeting at 5. I'll try to have some work here, or I'll email you, or I'll put a note on the door that says come an hour late, or whatever. We'll work it out, okay? I'll try to email you at the very least. So before you trek all the way over here, you might want to just check your email in case I said I'm going to be late. So that's, but I understand we're all busy, so that's that. Okay. All right. I think that's enough about the class logistics. All the reading assignments are on the back. Second last page in the back. We've already gone over reading, so I'm not going to berate you on that. Oh, a couple other logistics. Obviously, if you have to use the head or something, what's the closest one? Those little porta potties or something? Yeah. Something right across the street. Is there water right outside too? I think there is. Just get up and go. I mean, you don't have to raise your hand. Yeah, I mean, we're all adults here. Try not to run over the video camera on your way out if you do leave. But we're all adults here, and you guys can come and go as you need to. Okay? All right. Any questions about logistics of the class? No? Okay. All right. So when I first put together the syllabus here, I said, these guys are going to do 4 projects and blah, blah, blah. And I kind of got to thinking about it, and I said, I'm not going to have you guys do like weekly homeworks where you have to type and do it all. I said, well, let's have the projects. Then I realized this Mastering Physics website has the ability for me to give you homework that's graded all on there and everything. And it's probably, if you're going to do well in the midterm, you might want to do some practice for the types of problems you'll see. So I kind of think it might be better to do kind of a half and half sort of thing. Here's my idea. We can have a discussion about it if you want. What if we had, say, 1 or 2 projects and then more or less weekly homeworks? What do you think about something like that? Anybody have any idea, any thoughts about it?
I think combination would.
Combination would be all right? Okay, that's one idea. Anybody else?
I agree.
Agree, combination? Okay, here's what I'll do. I actually don't have homework for you tonight already because I just kind of wanted to get today out of the way and we'll go. But I may email you with some stuff over the week. But sign up for Mastering Physics, and I'll get the course information to you and email you. Did everyone get the email from me a couple days ago? Okay, good. So we're all connected on email. Feel free to use that to email me, especially if you have any questions about the thing. So we'll do a combination. I'll work the details out over the next few days, let you know. Okay, let's see. Eric, you falling asleep? It's tough. I know. Sorry. This beginning stuff is a little tricky, and it's a long day. Try not to fall asleep if you can. Okay. So, and by the way, if you need to stand up in the back, by all means, typical kind of military thing. Just feel free to do that. Tom.
Quick question about the mailing list.
Yes.
Can I give you my personal email also?
Sure.
Because I only get my work email.
Oh yeah, absolutely. If you guys email me from whatever email account you want, and then I'll switch it to the mailing list, so I'll email you on the whatever account you want. Okay? All right. Now, on to physics. Oh, by the way, we will have breaks. So don't worry. There will be breaks in here. 3 hours is way too long to sit here and listen to me, even if I'm doing fun stuff, which I haven't yet. So we'll get there. I did tell that fun joke. Want to hear an Air Force joke?
Sure.
The Air Force is a joke. Oh, sorry. Okay. Yeah, I know. Coast Guard. There's no Coast Guard people in here, right? I can't give all my jokes at once. I'll tell you about that one later. Okay. So if you look in your book, there are four. Actually, what I didn't put. I thought I had this in here. There it is. There are four different types of, or four broad topics we're going to talk about: physics, chemistry, earth science, and astronomy. And we're going to do it in that order, namely because that's your textbook order. Okay, but also because I think it makes sense to do it in this order because of the way things build on each other. Okay, and we'll kind of get to that. Physics is, I like to say physics describes the entire universe. Okay, and you can say, well, then what's the difference between chemistry and physics? Well, I might agree with you to some extent. Chemistry is about how various atoms interact with each other. Now, physics describes that, but chemistry gets into a little more details about specifics. We're going to start with physics because chemistry builds on it. And then earth science builds on physics, builds a little bit on chemistry, depending on where as well. And then astronomy, well, yeah, I guess it builds a little bit on chemistry and physics as well. But mostly, physics is kind of the initial one. Okay? So physics describes the universe. Now, let me show you what I mean about conceptual physics and the kind of ideas we have when we talk about concepts. Okay, put on your caps, thinking caps right now, okay? I have this nice microeconomics book I got from the shelf over there, okay? And I'm going to try to beat it up a little bit. If I take this book, right, it's a real book, and I drop it, like, to the floor, okay? What's it going to do? Ideas. It's going to fall. It's going to accelerate. Interesting. We haven't talked about acceleration. That's interesting. Okay. What do you mean when you say that?
As it drops, it's going to be increasing in speed.
It's going to be increasing in speed. Everybody agree with that? Like right now it's not moving, and then by the time it hits the ground it's going to be moving faster? Good. Very good. Okay. So it's going to drop. What's it going to do when it hits the floor? It's going to make a noise, decelerate. Okay. All those ideas. So we know what's going to happen when we drop this. Okay. Ready? All right. All right. Was anybody what's the word? Confused about that, or like surprised, I should say. Anybody surprised at how that happened? I hope not. Okay. Well, we've all been on Earth for 20 plus years. Okay. And what's that?
Gravity is a fickle.
Yes, gravity is indeed. All right. So that was the book. Okay. Got a little bit of mass, whatever. I did the same thing with this University of Maryland University College course evaluation. Okay. What's it going to do? It's going to go down a little at a slower speed. Okay, Tom?
I agree.
Okay, is it going to go just slower like this, or what's it? No, there we go. Okay, so Eric said it's going to go like this.
Yeah.
Okay, so we all drop pieces of paper, right? Okay, well, what if I did this? Different story, right? Well, let's see. Here's the first one. I grabbed two. All right. Okay, Eric was absolutely right. That's what it's doing. Okay. Question is, why does it do that? And by the way, the same exact piece of paper basically, right? I crumpled it up. Is it going to do the same thing? No. No, it's going to kind of go foomp, just like it did, just kind of like the book in some sense, maybe a little slower, right? So something is different about that. So yes, gravity is fickle, but gravity seems to act a little different on these two things, right? Okay, so see how we're kind of talking about concepts? I mean, I haven't used a number yet, right? No numbers yet. All right, not even going to worry about it. What would happen, though, if I take the book and the piece of paper, and I put the piece of paper underneath the book, and I drop it like this?
The book will go straight.
You think it's going to separate? So you think it's going to go like this and going to go maybe like that? Okay. Who thinks it's going to go like this? No, both. No? I mean, it's an idea. If we just had a hypothesis, you all know about a hypothesis, right? Which is, maybe what could happen. Might be. It's probably not. You're probably right there. Okay. What else? What are some other ideas?
Straight down.
Straight down. So you think the book is going to go, boom, push the paper down?
I don't think the distance is great enough for it to affect paper.
What if I did it from up here?
Possibly.
Possibly? Okay, let's find out. Okay. Okay, straight down, pretty much. Okay, it's not too surprising. All right, so far so good. Okay, so let's see. We've tried it with the book. We've tried it with the paper. We tried the paper under the book. what's going to happen if I now do the piece of paper on top of the book? Separate? You think it's going to separate, Louis? Okay. You think it's going to stay together?
No.
You mean it's going to go foom, both like that? No? We'll find out. Okay. So, okay, again, could it go like this? No, it's probably not going to do that, right? Okay. All right. Maybe I should wait till later. No? All right. All right. All right, here we go. Okay, ready? Did you guys see what happened? Stayed together. Okay, now, was anybody surprised about that? Oh, come on. You guys were all saying, oh, it's going to separate. There's no way it's going to do that. It's called surprise. Let's try it again so I wasn't lying to you. Okay. Question is, why is that the case?
Air resistance.
What about air resistance?
When you're dropping the heavy object, the weight of the object is more than the air resistance, so it falls.
Okay, but why doesn't the piece of paper, why doesn't it do like...
It's on the book is taking the weight of it.
It's taking the weight of it. Well, hold on. So, okay, so it's taking the weight of it. Interesting. I'm curious what you mean by that again. Try to explain it a little more. When it says it's taking the weight of what?
The surface of paper on top of the book is stopping the air resistance from hitting the lighter surface.
On top of the, okay, there. That sounds a little better. So what? Brent?
Rank.
Sorry?
Rank. Like Frank with a B.
Oh, Brank. Because your last name is. I get it.
Yes.
Hang on. Brank. Okay. All right. So what Brank is saying is that there's this air resistance piece, and the book is somehow moving the air out of the way, maybe? Okay, who thinks there might be some other explanation?
I think it might be a draft swirling up underneath from underneath the book.
I see. So you're saying that maybe the air's coming, it's getting pushed out and then coming and pushing down on there?
Because the air has to refill that space that is being taken up.
That's a good point. There's probably some of that. But I think Brank's got the right idea here, where the book, it's pretty heavy. Its ability to push air out of the way is pretty. Air is not very heavy. We all know that, right? I mean, we breathe it in every day. And it's not like I'm all of a sudden heavier. I mean, you are, but you don't really feel like it, right? And I guess technically, if you're in water, you'd actually float a little better. So, but the point is that yes, the book is pretty good about pushing that air out of the way. And if the paper doesn't have any air to push down on it, why would it do anything other than go down at the same rate, right? Well, it's a little more subtle than that, but we're going to get into some more details about that. But that's kind of an interesting one, right? You guys probably, some of you probably never even thought about the fact that, oh, yeah, okay, so this thing goes down because there's air resistance. We know that. That wasn't surprising. But when you take away the air resistance, it goes down as fast as the book. Pretty cool, okay? That's what I mean when I talk about conceptual physics and kind of our ideas going forward with that. Okay? Questions on that? Okay, was that hard? Was there any no math, right? No, I don't think we said any numbers that whole time. Good. Not that math is bad. Math is actually a good thing, but that's it. Okay, so we're going to start, what we just talked about was a little bit about motion, okay? And Tyler said, hey, that book accelerated. Well, by the end of tonight, we're going to talk about acceleration. But we got to start with some other concepts about motion first. Okay, and this was in your book. Hopefully you got to at least read it. There's this guy named Aristotle. He was on Earth living like over 2,000 years ago, right? 2,300 years ago. Well, actually 2,384 years ago, or 80, whatever, 94, 97 years ago. Okay, pretty smart dude. In fact, one of the smartest dudes in that era. I mean, he did a lot of science. Not necessarily the kind of science that we talked about. In fact, he probably didn't do much dropping of things, which we'll talk about in a reason we'll talk about in a second why we might know that. Okay, but he did think about things and tried to formulate why the Earth and the sky and the sun and everything else behaves the way it does. Here's what he said here's what they had to say about that. One of the most important figures in Western philosophy, profoundly shaped medieval scholarship and on physics and physical science. Okay, And the influence went straight up until we really figured out what the heck was going on. Okay? Smart dude. Too bad he was wrong about some things. Here's what he thought. Okay? Number one, he thought, hey, there's this two different kinds of motion. And when we talk about motion, we're just talking about things moving. And he looked around and he said, well, things are moving. Why do they move? Hey, here's why. Number one, things have their own type of motion. Okay? Things like rocks and people and things, they want to be at rest. Like that's their natural state. Right? That's what he thought. Stars. Well, did he ever see a star stopped? No. If you look at a star now and then turn your head for an hour and look again, it's moved. And it does that continuously, and the stars never stopped. Okay, neither did the planets, although they moved in weird positions. Okay, smoke. Well, what does smoke do? It rises up. So Aristotle said, hey, smoke, its natural state is to be rising up. Okay, all right, well, not really the case. Okay, he didn't think about the fact, oh, there's actual cooler air underneath the smoke, et cetera, et cetera. Okay, here are two big beliefs of his. Heavier objects fall faster than lighter objects. So he said, look, if something's heavier, it's going to fall faster than something that is lighter. Okay, what's that?
Outside of a vacuum.
Well, he just thought in general. And this is part of the reason that we realized he probably didn't do much in any of these experiments. There really wasn't that idea of experiment. And the second belief of many was that moving objects, in order to keep moving, you have to have something pushing on them or pulling them. Okay, and that one doesn't sound so weird. To tell you the truth, I mean, first glance, you think, all right, look, something has to be, if it's going to move, we got to keep pushing it, right? If I took a chair and pushed it, well, it stopped, right? And I didn't keep pushing it. So if I wanted to keep it going, I'd have to keep pushing it, right? Well, that is one of the things he thought. And that one doesn't sound so weird for what it's worth. Okay? Those are his two beliefs. Okay. Well, believe it or not, his beliefs were not really correct. Okay? Along came this guy Galileo. Now, you've all probably heard of Galileo to some extent. Another really smart dude. Another dude who, unfortunately, had a lot of great ideas that people didn't like because they went against their religious ideas. And unfortunately, we still see a lot of that today. But that was one of the sad parts about it. But this guy was great. He really founded science in terms of the science we know today. Okay? One of the things he said was, look, do heavier objects fall faster? Well, Aristotle might not have tried it, but Galileo went and said, I'm going to try it. Okay? And let's see, I forgot to bring two objects that I'm going to, well, let's see. How about this book? No, we'll try something else. Something that's a little lighter than the book. How about this? Pen. Here we go. Okay. Everybody agree that the pen and the book are probably not the same weight? I'm going to make sure. The book's heavier, right? Okay. All right. If we're Galileo, it's a little tough to see here because I'll try to drop it out. I'll drop them on the table here. Yeah. Well, I'll drop them on this table here. Galileo says, let's test it, right? And let's see if this is going to be the case. So he takes two objects. Supposedly he went to the top of the Leaning Tower of Pisa. Cool place, by the way. That's not really, we don't know if that's a true story. Who knows? Kind of a cool story, though. I could lean over and drop these things. Okay, dropped two objects, took a big, I guess a big ball of something and a small ball or something like that. Dropped them, and they both fell at roughly the same rate. And I say roughly because if you do it far enough, air resistance does come into play, even for big, heavy objects. So he was off by a little bit. And actually, people claim, well, you're wrong, But he's like, well, come on, guys. I mean, this is like, we're doing this from way, way up high. Bear with me here. And he would try it again, right? And so you could try and see that heavier objects, as long as they're not light like a piece of paper, which really affected by air, they will fall the same rate. Okay? All right. So that's what Galileo said. All right. And Galileo did it, which is the important part. Okay? Well, both of the important parts. But the fact that he went and tried it is the part of science that we really like today. We can try an experiment, and we'll get to labs where we'll do the experiments, and we'll actually see how some of this stuff comes into being. Okay? So that's what Galileo said. Now, by the way, so that was the first thing that Aristotle believed that Galileo disproved. You'd think somebody else would have tried it in the, 1800 years between when Aristotle said that and Galileo did it, but nobody formulated it quite like he did. Now, here's another question. This is another one Galileo had. He said, does a force keep a cannonball moving after it leaves the cannon? Okay, you guys are all in the military, you've fired weapons before. You shoot the projectile, the bullet, the cannonball, whatever. Once it leaves that barrel, is there anything else pushing on it?
Nothing is pushing on it, but it's affected by gravity. And
It's affected by gravity, humidity. I'm not sure. I'm not sure about humidity so much. You know, I can't see like General Lee saying, "It's a little too humid out here. Don't shoot the cannon." But
it depends on the range you're shooting.
yeah, there you go. Well, no, that's true. But yeah, the question is, does there anything else besides gravity pulling down on anything pushing side to side, and maybe some air resistance? Besides the air resistance and the ground or the gravity, is there anything else pushing on the cannonball? We have to talk about that a little bit, okay? By the way, the answer is no. All right, there really isn't, and the ball keeps going. The cannonball keeps going. Interesting idea. So you need, so a force is actually needed to get the cannonball going. In other words, it's not going to go on its own. You got to have that exploding gunpowder, right, or whatever, that's going to start it going. And then once it's going, there's this thing called inertia that actually keeps it going. In other words, it has this property, and everything has this property, that once it's moving, it keeps on moving. And that's a weird concept. The first 10 times I heard that, I'm like, it just doesn't quite make sense. What is this idea of something keeps moving? And you've all heard the saying before, which we'll get to in a minute. But this thing called inertia is a property of an object. We don't know why this is the case. By the way, there's a lot of things we don't know the why of. We know how, we know that it does things. The why part, we don't really know why a force is not needed to keep something going. But it's the case. And you can actually demonstrate it. Well, we'll see some demonstrations here in a minute. Okay? Here's a little, what we call a thought experiment. In other words, just think about it in your head. Middle of outer space. There's no planets anywhere nearby. You're in the middle of nowhere. You take a cannonball and you go, boop, and you tap on it. What does it do? Does it go for a little bit and then stop? No. It'll keep going for as long as there's no other planets around. Okay? You guys are too young to remember this. I barely remember it. There's a spacecraft called the Voyager 1 and Voyager 2. It's a spacecraft that we launched in 1970, might be on the next page, 77, 78. Nope, not there. 77, 78, launched the spacecraft. It went out, it went spinning around the sun, and then took off for Jupiter and Saturn and all those cool planets out there. I don't know if it went near Pluto, but it went out there. And it's going about 30,000 miles per hour. And you know how big the rocket is that's propelling it right now? No rocket. It doesn't need a rocket anymore because it's in the middle of outer space. And in fact, it didn't need a rocket since it spun around the sun. What they did was they used the gravity of the sun to do this, what do they call it? Slingshot. Yeah, that's it. They used a slingshot to slingshot like they did in Star Trek or something. One of those Star Trek movies. Anyway, they slingshot the spacecraft around the sun, and it goes flying off. And if you do it right, it doesn't come back to the sun because of gravity. It just keeps going. And it's far enough away. It's got what we call escape velocity. And it's far enough away that it's never coming back. And it doesn't need a rocket anymore. Okay? By the way, it does have power still. Okay? Anybody know what powers those kinds of things? Not solar. You'd think it would be solar, right? But first of all, it's so far. Have you ever seen well, I don't really have pictures. I guess they might have pictures at this point. If you sat on Pluto and looked at the sun, it looks like a tiny little dot, believe it or not. Not like a star, but it's bigger than stars, but it's so small that you might miss it. Like you might scan around and go, oh, there's the sun. You know, it's like that small, just sitting on Pluto. So yeah, solar is a good idea, but it actually doesn't work so great when you're far enough away because solar panels, 1977, they weren't so good, number one. And number two, they're expensive and they have to be big and all that. What makes the Voyager keep broadcasting data back to us? Plutonium. There you go, plutonium. Believe it or not, it's nuclear fuel. It's got these big arms. I wish I had a picture. If I had internet access, I'd show you a picture. But look it up, Voyager spacecraft. It's got these big giant arms on it. And you think, oh, that's cool. I wonder what that's for. That's so that the heat generated by plutonium doesn't fry all the equipment. It moves the heat out and kind of sends it out into space. It's I mean, I feel bad for if like an alien someday goes, hey, look, a spacecraft, and then, you know, plutonium, like radioactive, but not going to worry too much about that. It's probably not going to happen. Space is huge, so we'll get to it at the end of the class. Okay, so anyway, tap a cannonball in the middle of space, it's not going to stop. It does on Earth because we've got lots of things going on. We've got air resistance. We've got the cannonball hits the ground and stops. It, like, you know, bangs into a ship and stops, whatever, right? If there was none of that, if it was a frictionless thing, and we do see some things like this, like ice pucks, right? If you talk about see an ice puck, you can do, I mean, anybody know about hockey? If you do icing the puck, somebody's sitting way down, you want to stall for time, you hit the puck, and it goes all the way to the end, and it doesn't, you know, it keeps going because it's so little friction. Same sort of thing in outer space. Okay? All right. So that's what Galileo thought. Galileo did experiments. He tried these things. I'm not sure he used a cannonball, but he did these things. Okay, next topic. Mass versus weight. Okay. In the US, one of the problems with being in the US is that we generally deal with pounds, and we deal with miles, and we deal with feet, and all that kind of stuff. The rest of the world, except for like 2 other countries, even England, English system, they don't even use it anymore, uses this thing called kilograms for your mass, although they get it a little confused with weight too. But we've got this thing called mass, which is in kilograms. And everybody's heard about that, right? Kilograms. Okay. Mass, which is basically the amount of stuff you've got in your body or in this pen or in this water, okay? Your mass remains the same no matter where you are. Okay, so if I'm here on Earth in Djibouti, I have a certain mass, and if I go to the moon, I've got the same mass, and if I go sit in outer space, I've got the same mass, right? Until I throw up because of seasickness or something, right? And I've got, or outer space sickness or whatever. But that's what mass is all about, okay? So mass is the amount of stuff in an object, the amount of quantity of matter, which is atoms and electrons and neutrons, all that kind of stuff, okay? And it's also a way we can think about this inertia thing, okay? If something has a lot of mass, it's harder to start moving and to stop moving, okay? And if anybody of you guys in the Navy and have been on ships, you know how long it takes to get the ship going, right? It takes like a mile before an aircraft carrier gets up to speed because it's hard to move that much mass. And then, trust me, if you try to stop a carrier in less than a mile, it's not going to happen, right? Because you can hit full reverse, and those engines are just turning, and the ship has just got so much mass, it keeps on going and keeps on going. Okay? Same thing with all other big objects. Tiny little things, easy to stop. Okay? So that's where we measure inertia, or we can compare inertia to the amount of mass something has. Okay? Then we've got this idea of weight. Okay? And anybody who's ever had to get weighed in somewhere knows about weight, right? You step on a scale and you weigh something, and that's in pounds normally for us Americans, right? But it's also in this thing called newtons. We haven't talked about Isaac Newton yet, but he's another famous physicist, brilliant guy. He had a unit named after him. If you're ever that famous to get a unit named after you, you know you did something good. And that's what kind of the equivalent of pounds is, and it's a measure of force. So if I'm standing on Earth, I might weigh 170 pounds, or I don't know what that would be, and I don't even know, 85 newtons or something, right? If I go to the moon, I'm actually going to weigh less. Same mass, less weight. Okay, everybody get that part? Okay, weight is strictly due to the amount of gravity on an object, which depends on where in the universe you are. Most of us spend most of our time on Earth. You can do that. Any divers in here? Scuba divers? Yeah? Okay, when you're underwater and you get all buoyant, right? It feels like you don't have any weight. You still do, but you've got equal force pushing up and down, and it's kind of cool, right? But we don't feel that very often. We always feel weight. If I drop the pen, right, it has weight because gravity's pulling down on it, and it's getting that force. Gravity's weird. We'll talk about that a little bit later. Okay. This is the kind of thing I might ask you on a test. What's the difference between mass and weight? And you have to go, well, look, mass is the amount of stuff and matter that an object has. The weight is the amount of gravity on it. Okay? Things like that. Not hard. No numbers yet, but we'll do it. Okay. Aha. Finally, my demonstration. Nicholas saw me putting this together in here. Everybody see all the way over here? Actually, you know what? Tell you what, Tom. could you go up and turn the camera just so it shows, just so you can see over here? Okay. Hopefully this will work. I haven't tried it in this. Tell you what. Could you just hold this down so the chair doesn't go flying when I yank on that little string? maybe that's it. Okay. Let's see. Let me try it. Let me just put this together here again. Sorry for the delay. So what I did was I took a little piece of string, and I had to, you know, a string comes in little strands, and I took the piece of string and I pulled off a couple of strands so it was pretty weak. And then I tied it to these giant batteries. Oops, shoot. And it's not going to work. It's not going to let me do this here. What I did was I put a string on the bottom and a string on the top. And I want to show you, if this works, the difference between when something's affected by inertia and when something's affected, when something's affected by inertia and when something's affected by weight. So could you stand up here, just hold this. Hopefully this is going to work. Okay, I'm just going to hold this up. String on the top, string on the bottom. Okay? I'm going to show you, hopefully, that there's one way I can break the top string and one way I can break the bottom string, and they depend on totally different ideas. Okay? Here's what I'm going to do. I'm going to try this first. Hopefully it won't break. If I yank down quickly on this string, this set of batteries has a lot of mass, right? It's pretty heavy. I'll pass it around if you want, but it's 8D batteries, which have a lot of mass. And they're Duracells, so you know they're like, you know, they got lots of mass in them, right? If I yank on this string, how hard is it going to be to move the batteries compared to yanking on like a penny? If I had a string on a penny and I yanked it, the penny would go foomp and fly, right? If I yank on the batteries, what are the batteries going to do?
Resist.
Well, they're going to resist because they've got a lot of inertia and they've got this resistance to motion. Okay? So the top string has to hold up the entire weight of this thing. Hopefully it won't break. Okay, and if I yank this, see how the bottom string broke and the top one didn't? Okay, that was because of the inertia of these batteries. In other words, batteries have a lot of mass. I yank on the string. The top string doesn't really feel that yank because the batteries haven't transmitted that yank to it. By the time it starts transmitting the yank, that string's already broken. Fair enough? Okay, I was a little smart and put another string on here for another part of the demo, the next part of the demo here. Okay? Now, same situation. Instead of yanking down on the string, I'm just going to pull it kind of slowly and just increase the weight, increase the amount of pulling. Increase the amount of pulling. If I do that, watch what happens. Whoop. I didn't even have to pull very hard at all. I just had to touch it, and the top string broke. Notice the bottom string still fine. Okay? Why is that the case? Thanks very much. Why would it be the case to do that? Tom, what do you think?
Because you have the weight of the batteries already, and then you were increasing the inertia.
Yeah. So with this, how much tension, which we'll get to a little later, is in this string right now? This bottom one? Nothing, right? So it could sit there all day. It's never going to fall off on its own, right? I don't care how many little strands you have. The top one, just like Tom was saying, was holding up the entire weight of these batteries. That's why it broke, right? And so when I started pulling down on this little guy, this didn't have much tension, but this top one had a lot of force pulling down on it, and it went snap immediately. And that's why it fell off a couple times before that. When I yanked on this one, different story. Okay, so do you see how same sort of thing can happen? I mean, I can yank that. I mean, it's easy to break, but it's just a matter of when does inertia make a difference and when does your weight make a difference? That's kind of a interesting way to think about it. And that's the one there. Okay, so this is the kind of thing I would ask on a midterm or a final. If I had this diagram and said, when I pull down slowly, which string breaks? And you'll tell me, oh, the top one does. Why? Oh, because the weight of the whole heavy ball is pulling down on it. Those sorts of things. Make sense? Not that hard. It's just, you got to think about it. Okay? All right. Okay. Now we've got this idea of mass and weight. And then we got to just throw in this. I'm not going to talk too much about it. Volume. Okay? What is volume? Anybody remember what volume is?
How much something takes up.
There you go. Okay. Frank says it's how much something takes up, how much space something takes up. That's the amount of volume on it. Totally different than mass. Okay. Now, could be related, but not always. Okay, this little thing of batteries, okay, has a pretty good mass, and you would not want to drop kick this, right? Okay, if I go and get a pillow, sure you drop kick a pillow, but it's got so much more volume, but actually less mass. Okay, if you are in outer space, okay, if you saw two things of batteries look like this, and I told you one of them had, we took out all the battery material and we just put cotton in there, right? And the other one was real batteries, but you couldn't tell from looking at them, and they're the exact same size. How might you tell which one has more mass? You can't lift it because it doesn't have any weight in outer space. What's that?
Shake it and see which one has, it's more difficult to change its inertia.
There you go. Exactly. What were you saying?
I said that which was going faster.
Well, how would it be going? You're sitting in a spacecraft floating around, right? And they're just both sitting in front of you. They wouldn't really both be. They'd both be going about the same speed. Good idea. So, but you're right. If we shook it back and forth, I mean, I'm going to pass this around. Just shake it back and forth and see how much energy it takes to shake back and forth. How hard it is to make it go this way, then stop and go this way, then this way. You used to do that in like elementary school, like gym class or something, right? You know, Christmas presents. Yeah, you can see how heavy they were by just shaking them back and forth, right? So do that when you go to cross. Shake it back and forth, and think about doing the exact same thing with like a pen, and go, oh, so much easier to do that. That's how you might tell if something's got different masses. Okay, different volumes and mass. Now we know the difference. Volume is just how much space, but it doesn't necessarily make sure, or it doesn't necessarily compare to the amount of volume. It can be just the different type of stuff. If you have if you have an item with a big amount of space and not much mass, we say it's less dense. It has less density than something with a lot of mass and a little amount of space, or little amount of space. Okay? All right. Okay, let me show you a couple little video things so you don't have to listen to me talk. Okay, let's see. The first one, oops. Oh, thanks, just put that right there. All right, these are the kinds of things you're going to see on mastering physics. Lou, you want to just shut the lights off there? And they're really, really short. I'll show you a longer one a little later. Okay, let's see. How am I going to do this? Ah, that's what I need to do. There we go. Okay, Newton's law of inertia. By the way, these videos I'm showing you are written by or done by the guy who wrote your book. He's even nerdier than me, believe it or not. Okay, you'll see when we get here. Hopefully this will come up. All right, let's see. Is this one? I think this is the one. There it is.
I got a couple of blobs. These are blobs of clay. These clays have inertia. Right now they're at rest. They tend to stay at rest. I put this clay on the top of my head like this, and I can see this one very clearly. But you know what, gang? I can't see this one back here. How can I see that one without touching? So if you turn around. Isn't that neat? Things tend to stay put. Do you ever do that? You got a bowl of soup, right? And you got the alphabet, and you want this alphabet over here near you, so you turn the soup bowl, and what happens? The alphabet stays there. You keep turning the soup bowl. Inertia. Things at rest tend to stay at rest.
That was the phrase that you guys hopefully have heard before. Things at rest, stay at rest. Things in motion, stay in motion. That's really the law of inertia, which we'll get to in actually the next chapter explicitly. But that's the idea of this. Things tend to keep going when you do it. Okay, so let's see. I'll show you this video in a little bit. It's another good one. Okay, where were we? Tablecloth. Okay, I wish I was going to try to set this up in here, but I couldn't do it. You guys know what I'm going to do, right? Or going to show you. If you take a tablecloth, there we go. You take a tablecloth and you put it underneath a bunch of silverware and dishes and stuff, and you yank it really fast, and you're lucky. Doesn't have to be that much luck. See what happens.
And what do we have down here, gang?
And he uses
We have
gang a
some
lot.
plates.
Okay.
No staples, no Velcro. The tablecloth. This is what I want you to do over the weekend when you get invited to dinner at someone else's house, okay? What you do is they say, hey, what are you learning at the university? Say, I'll tell you what I've been learning at the university. Okay? And get the table all set. Grab the tablecloth like this and say, do you believe in the first law of inertia? And they say, yes, we do. Gee, how about that?
Okay, so there's some inertia. A little tricky. I've done it before successfully. It's definitely scary. I mean, you think, oh my gosh, what am I going to do? Okay, inertia of a cylinder. Okay, let's see. Oops. All right. Can you guys hear okay? You're all right.
So what's the force keeping that going? No force. We don't know why it keeps going. But we call that ignorance inertia. Get the idea? Nobody knows why it keeps going. We just know that it does. And so we call that inertia.
Okay, so that's inertia. We already talked about that. What's that?
We don't know what it is.
We don't know what it is. Well, and that's really one of the things about science in general. There are a lot of things we don't know why, and I think that's kind of cool. I mean, we can always keep asking questions about, what's going on, and look, philosophy is the why part sometimes, So if yeah, exactly. Exactly.
Never again. Get out.
All right, let's see. Hopefully, where is this one? Anvil. Did anybody watch this one already? I don't know if you saw this one. This one's great. I've seen another video where he does this, and it's a little different, but this one's pretty good. Oop. Okay.
This has got a lot of mass, gang. To say it's got a lot of mass, and say it's got a lot of tendency to stay right.
It's an actual anvil. Hammer things on.
Yeah, I'm going to lay on here. Would you put the anvil right on my stomach, please? Right on my chest.
Acme anvil, yeah.
Okay, right here. Okay. Now, would you get on the other side and slam that thing as hard as you can? Over here, Troy. Oh, please don't miss the anvil. Do you have any grudges against your teachers? Hit it harder.
Now, what he says is afterwards he says, "Oh, I'm fine," and he said, "If I took a little quarter and let him do that, no, there's no way he'd let him do it. He'd crush his rib cage, right?" But the anvil, it's the same thing with the battery thing. Anvil has a lot of mass. When he slams that hammer down on it, the anvil doesn't really want to move, right? It just doesn't. It has this tendency to stay where it is, and so it's hard to move, and so therefore it doesn't actually transmit into his rib cage, and he's fine. I mean, I assume he's fine. He didn't die there, but okay. So anyway, that's that one. All right, only a couple more things here. Oh, you know what? I'm going to give you a break at just the wrong amount at wrong time. It's all right. How much is this Newton thing we're talking about? A Newton, 1 kilogram on Earth is about 9.8 newtons. We always round that to 10. I guess this is the first number we've used, huh? Don't worry too much about it. We're going to use 10 a lot. Why? Because it's easier. And that is not to say that I'm like dumbing it down. It just means, look, if we want to talk about how things, how much things are, why use hard numbers when we don't have to? You want to use the real, 9.8, I don't care. But we're going to just round it to 10, right? Okay, 1 kilogram on Earth is about 10 newtons. Okay, what that was. And we won't use pounds in class, but 1 kilogram is about 2.2 pounds. Okay, is a kilogram. Again, I'm not going to make you memorize those numbers. Just think about it when I say, oh, that's about a kilogram. You go, oh, that's about 2 pounds. Something like that, right? On the moon, though, remember, weight on the moon is different. 1 kilogram is only 0.37 pounds. So you can see it's 6 times less, actually. Okay, and in outer space, there's no weight, right? So there's no weight. So 1 kilogram is no pounds, really, unless you got to be pushing on something to give it a force or pulling on it. Okay, and 1 pound is actually about 4.5 newtons wherever there's gravity. So if you're on Mars and you're standing there and you weigh yourself and you're like, oh, I'm 10 pounds, well, that means you're 44 newtons. Okay, so that's how it translates over. So I did it backwards the other time. It's actually about 4.5 times more newtons than your weight. Okay, And this way is the one you divide by 2. Again, don't stress about that. OK. Anyone know what that is? That's a break. It's a disk break. So how about at 6:30 we come back?